So I think recording started. So hello everybody, and welcome at this special time of the Prague seminar. As you might anticipate it, we are back again with a new bunch of nice speakers. Today we have Simone and Noja. And Simone warned me that even though his old family tree reached to the Middle Age Spain, his name is Noja instead of Noja, as I had expected. But more recently, Simone is a postdoctoral researcher at the Heidelberg University, and presumably he prepared for us a very nice topic for today. I try to not mismatch the title. Pure Spinors fields. No. Nilpotence varieties, pure Spinors fields, and the Supersymmetry. So we're very glad, Simone, that you're visiting Prague, and the floor is yours.
So,
okay.
Let's go. One little presentation.
Adjustment.
Yeah. Present. Yes. And I guess back and forth just like.
Oh. Okay, everything is I'm fine. Share content. Start recording. Nobody takes care. Everybody's there.
Fine.
They somehow expected it.
So they really enjoy the first part of the talk.
What?
They really enjoy the first part.
It's like the best part. Okay.
So I'm now a little bit afraid to touch it, but let's. Yeah, that sounds like it sounds like a good news. So okay, so thank you very much again for the very nice introduction. So yeah, I'm Simone. Today I'm gonna report on a project of mine and some collaborators. So the generic title of this talk is Nilpotence variety, pure Spinors superfields, and supersymmetry. And allow me to start with some, again, generic consideration on supersymmetry.
I don't know if it's for everyone, but we don't see the slides.
So that's, I guess that's an important remark. So perhaps you need to share the screen.
What now?
Now I see them. Thank you.
So it's fine now. Okay,
Thanks.
All right. So perhaps reduce to icon. Yes. Okay, great. So allow me to start with some generic considerations. So as one deals with supersymmetric field theory, so one faces some essential difficulties. So among these, one is that supersymmetry is sometimes only represented on shell, and the second one is that supersymmetry sometimes is only represented up to gauge transformation. So this lead to many problems. Among these, again, there are problems with quantization, but what we'll be actually interested in this talk will be a geometrization of the theory. So the point is that it is reasonable to think of supersymmetry as arising from the action of a particular geometric symmetry on some space in the very same way. For example, one think about Lorentz transformation as a symmetry of Minkowski space. And in order to see something like this, you need to enlarge the Euclidean space to Minkowski space. So this leads to this leads to wonder which kind of space do you need to have something like this, and the answer is that you need to basically extend the geometry to allow also for fermionic direction to see this particular symmetry as a geometric symmetry of the theory. So in other words, you should look for a superfield formulation of the theory. There are many different paths to superfield formulation. So in the slides, I actually list 3 of them. So one is the harmonic superspace, pioneered by Galperin, Ivanov, Olszewski, and Sokachev. So there is a rheonomy approach which works particularly well when one considers supergravity theory, and pioneered by Castellani da Refre, now Antonio Grassi and collaborators, for example, Carlo Busier. And third approach is the so-called pure Spinors, first introduced by Nilsson and Howe, and more recently by Berg. So what I'm going to do in this talk is to give a view, let's say a particular view, a particular perspective on pure spinor superfield formalism, which is on the one hand amenable to mathematicians, but on the other hand, it actually yields a notion of multiplets as understood by physicists. So I'll try to stay somehow in between. So how about the structure of the talk? So I'll start with a definition of what I mean by multiplet. Then the bulk of the talk will be about the definition of geometric space that I'll call Nilpotence variety, and I'll introduce the pure spinor superfield formalism, which relies on this particular geometric space. I'll try to provide you with as many examples as possible, and if time permits, I don't think this will be the case, I'll try to give some general results that can be obtained by a projective and derived geometry. So, all right, so this is basically the byproduct of a long-standing project going on with this collaborator that you see on the slide. In particular, there's a paper out and more to follow within the next, hopefully, weeks. So, okay. So I'm going to start with some mathematical light fathoms, so introduction of things that we will need. This is a little bit clumsy because, as a matter of fact, among the audience, there are people who knows these things much better than I do. So I'll be pretty quick. So the first definition, basic one, is the notion of DGS vector space, where DGS stands for differentially graded super vector space, which is just the Z cross Z2 graded vector space, which is equipped with a square zero differential of a certain pi degree. So you can conveniently pack this information into the notion of a cochain complex in the category of super vector spaces. First, you have a notion, you can imagine, of total parity. And if you, in fact, the meaning of the Z cross Z2 grading, so physicists call the Z grading ghost number, and the Z2 grading intrinsic parity, fermion number modulo 2. So given a DGS vector space, one can think about an L-infinity algebra structure on this space. This means that you have a collection of multilinear map, again, of some given pi degree, and they satisfy 2 properties. So the first property, 2 actually very complicated properties. So the first is a greater skew symmetry. The second one is a higher Jacobi identity that generalizes, of course, the ordinary Jacobi identities for Lie algebra and Lie superalgebra. So, of course, this might appear very complicated, but once again, you have a very convenient way to pack this information into something else, more handy. So the datum of a super infinity algebra turns out to be equivalent to a square zero derivation on the coordinate algebra of G at a certain shift in the Gauss degree. So basically, you're considering this coaching complex that you see on the slide. So some examples just to make contact with things that everybody knows. So if G is supported in purely even parity, of course, one gets an ordinary infinity algebra. If G is supported in 0 degrees, so no what part one, no higher things, one just get the notion of super Lie algebra. And if the multilinear map UK are 0, for k greater than 0, one gets the notion of a DGS Lie algebra. And there's DGS Lie algebra that everybody knows. And that's just the DGS Lie algebra of the endomorphism of a DGS vector space, where the non-zero bracket M2 is given by the commutator. We'll use this. So, of course, there's a notion of maps, so L infinity maps. So these objects are indeed objects of a category. And well, given a map, one can think of an action. So one can think about an action of an L infinity, super L infinity algebra on a certain DGS vector space. Okay, and you can write an action through indeed an L infinity map just like this. So far, this is just algebra. So in order to somehow move toward physics, we need to move on a manifold that will be thought as our space-time. So somehow one needs to make all this algebraic notion relative to points in space-time. So the analog of, from this point of view, the analog of a DGS vector space is, of course, the DGS vector bundle, meaning that you can move on a base. And a DGS vector bundle is, again, a pair, ED, on X. And this is basically a Z cross Z2 graded vector bundle, which is a kit with a collection of differential operator that acts on the section. And this differential operator squares to 0. So notice that this is not the notion of flat connection. So this is something else. It's closer to, is actually closer to homological algebra. Okay.
So you have any condition for the order of the direction of the.
Sorry? Oh yeah, I guess it's like 1 plus, something like that. The pi degree. Yeah. Yes, I think so. Thanks. That's the good question. Once again, so we will focus on a particular kind. So I actually introduced this early on. A DGS Lie algebra, which was the DGS Lie algebra given by the endomorphism of DGS vector space. So we will consider in particular subalgebra, which is a subalgebra realized by a differential operator. So X is differential operators, and here P curly E are the section of a DGS vector bundle. So we will be interested into this gadget here. So it's a particular subalgebra. So allow me to introduce another notion that somehow will be the basic notion that we will use to introduce a definition for a multiplet, a G multiplet. So the notion of a local G module. So local G module is a triple. So ED rho, where again ED is the DGS vector bundle, and rho is a super L infinity map. So basically an action by a differential operator on this DGS vector bundle. So you can unpack this action concretely. So the data of rho are a collection of maps that goes like this and satisfies some compatibility relations. And one immediately understand what this relation means if one looks at the lowest of this. So the lowest reads like this. So you can see that if row 2 is 0, you have a strict superly algebra action. But if row 2 is not 0, well, then row 2 is homotopy, which corrects the failure of row 1 to be strict. And you have a similar interpretation for higher terms. So the higher terms are basically row 3 will be an homotopy for row 2, so on and so forth. So why so? Well, again, because supersymmetry might be only realized on shell or up to gauge transformation. So these higher order terms basically correspond to closure terms, which corrects row 1 by, for example, gauge transformation or a contribution that might be proportional to equation of motion. So the L-infinity structure that basically come around to this keep tracks of the non-closure of the symmetry algebra. So that's the main data. So we're still missing one piece of data to move toward physics, which is basically the symmetry of the space-time. So basically the affine transformation. So we will only deal with flat space-time, in particular complexified flat space-time. So our space-time will just be CD, so the copy of the complex plane, and the complexified Poincare algebra is the same direct product of the translation, B, with, well, if you want, the Lorentz transformation, the complexified Lorentz transformation. So a particular notion of vector bundle, which somehow keep track of this, the existence of this affine transformation, is called affine vector bundle. So an affine vector bundle is basically a vector bundle that carries an action of the affine group or the affine algebra in a way which is compatible on its section, in a way which is compatible with the neutral action on the base. Okay, so in other words, we're requiring, again, this is a compatibility condition, so we're actually requiring that diagram commutes. We'll deal with this vector bundle to encode information of the affine transformation. So finally, what's a G-multiplet? Well, a G-multiplet is a local G-module structure. So once again, this is triple with, again, a compatibility condition on the action. So what we're asking is that the action of the affine transformation seen through the L-infinity algebra G coincide with the natural action given by the basically affine vector bundle structure. So in other words, this sounds very complicated, very abstract, but in some sense, so philosophically, it only says that somehow multiplets, so this notion, this apparently very abstract notion of multiplets, is something that leads to study superalgebras that contains the affine algebra, so the symmetry of the spacetime, as a subalgebra. And of course, we realize this multiplet as a collection of section of some DGS vector bundle, which transform in some way under this this particular symmetry encoded by G. So there are, of course, many obvious examples. So the first example is just to basically consider the direct product of some Lie algebra with the affine transformation of V. And this leads to the notion of so-called flavor multiplets. But there are also other examples. So for example, if you consider the conformal transformation, they obviously contain the affine algebra of V, and you get a notion of conformal multiplets. So the notion we will be interested into this talk will be the case of super Poincare algebra. Of course, super Poincare algebra contains the affine transformation of the spacetime. And the notion of P multiplets will recover the notion of super multiplet as known in physics. So how to do that? We'll do that by using this pure Spinor formalism or super Poincare algebra. So this machinery, of course, you might complain about the word machinery. Hopefully, I'll make it a little bit more precise in what follows. So this machinery is something that out of the data, out of a geometric data, so a sheet of modules on a geometric space, construct a multiplet. Okay. Right. So this geometric space is indeed the nilpotence variety related to P. So what is the nilpotence variety of super algebra? So super algebra has graded 0 part and graded 1 part, so even an odd part. So you can start by picking out an odd element, Q, and you can consider the commutator of Q with itself. Let's just call it like Q squared. And you ask that this is 0. So if you think about this for a moment, you would realize that this defines a set of quadrics. And the 0 locus of this set of quadric is what we call nilpotence variety, or better affine nilpotence variety. So, of course, might be convenient to think about projective nilpotence variety, which is just a projectivization of this affine space. And this makes sense because the equations are all homogeneous. Okay, so the base of solution descend to something that lives in a projective space. So this is not a new beast. So it appears under different guises in pure mathematics. For example, in the world of Gruson, Duflo and Serganova. So for example, Duflo and Serganova call it associated variety of a Lie superalgebra, and they introduce it in relation with representation theory of Lie superalgebra. So there's something called Duflo-Serganova functor that uses exactly this construction, exactly this space. So from the point of view of physics, if you think about it, you can interpret, very roughly speaking, this variety as a moduli space of cohomology, because in a sense, it parametrizes supercharges which square to 0 and hence define a differential. So this cohomology in a, in physics, in a contemporary physics are called twist of the related G invariant theory. So you do actually compute this cohomology basically on the BV complex of the theory. So why is this useful? Well, because a supersymmetric field theory might be incredibly complicated. So it might be incredibly hard to extract information, but a twisted theory, so the twist, so the cohomology that get out of this procedure might be, for example, considerably easier. It might be an holomorphic field theory, or might also be a topological field theory. And the twisted theory, the thing is that the twisted theory still retain information about the theory. So as somehow as cohomology retain information, some crucial information about the complex or the manifold that you're looking at. Right. Let's go on. All right. So just to make things a little bit more precise. So a more formal definition of nilpotence variety. So you can think about R being the basically the polynomial ring given by the algebra coordinate of G1. And from this point of view, you indeed might define I to be the ideal, which is defined by the set of equations given by the commutator of Q with itself, where Q is a point there equal to 0. And then you would call spec R mod I, so this quotient of ring, the affine nilpotence variety, and proj R mod I, the projected nilpotence variety. So let me stress that the data of nilpotence variety comes automatically with an embedding. Very concretely, what you can do if you like work with your bare hand is to expand a charge Q, and basically consider the quotient that you see in the slide. So the ideal, which is basically defined by lambda, gamma. Lambda is sometimes called pure spinor constraint, and it's what basically cuts out this nilpotence variety. So go on. As I said, I'm interested into this construction for a specific case. So the case of Poincare superalgebra. So just to review a little bit the structure of a Poincare superalgebra. So of course, it comes with a C2 grading. One has a fermionic part and a bosonic part. And what's inside the fermionic part? So you have, in general, a tensor product of a spin representation of V with an auxiliary space, auxiliary vector space, which can be or not equipped with a symmetric or anti-bilinear form. And somehow the degree of supersymmetry, so curly n, is the dimension of U, is related to the dimension of this auxiliary vector space U. So the bosonic part, of course, arises from Huffman transformation. So you have the ordinary Poincare algebra. So semi-direct product of V with the one Lorentz transformation, plus another part, which we call R symmetry. And R symmetry are nothing but the automorphism of U. So as you can imagine, since U can be the symmetric or antisymmetric bilinear form, this might be, well, in the very case, just QL of U, SOU, or SP of U, in case we have a symplectic form. So there's a very important sub-algebra, which is a so-called supertranslation algebra. So this encodes, well, in a sense, translation together with the odd part of the Poincare superalgebra, and more precisely, it can be described as a central expansion of V1, so the odd part by V, by the translation. And on this guy, we have an equivalent map, gamma. Of course, I haven't called it gamma just because I like the letter, but because this is, of course, related to the gamma matrices. So in a basis, this will become the ordinary gamma matrices. So it is convenient for our purpose to look at this as to look at the Poincare superalgebra as a graded algebra, and it is convenient to define it in a way that supertranslation are positively graded. So from this point of view, the map gamma is a P0 equivalent. So example of this variety, this Nilpotence variety. So this is probably the first. So this model D equals 4 n equal 1 is probably the first example of supersymmetrical theory that you would encounter when studying supersymmetry. And in this case, the super Poincare algebra is, as you can see in the slide, so you don't have any auxiliary vector space. You have the semi-direct product with, well, of course, the ordinary Poincare algebra, and in the odd part, you have the direct sum of two Weyl spinors, so Weyl and anti-Weyl spinor, two-dimensional. So in this case, you discover that gamma defines an isomorphism of S plus tensor S minus into V. So if you think about it, this implies that the pure spinor constraint, so the ideal that we're looking at, so basically you're on that locus, on the locus Q with Q commutated with Q equals 0, if and only if Q is either in S plus or in S minus. So this means that basically, since S plus and S minus are two copies of C2, so C2 planes, that the nilpotence variety, the affine nilpotence variety, simply consists into C2 planes in C4, which intersect at the origin. So you start seeing that in general, this variety is singular. Of course, the projectivization of this is just the two disjoint copy of P1. So you project it per place.
Just wanted to understand if I understand correctly. So this nilpotence variety is like the coordinates on this space are the pure spinors.
If you want.
Lambdas.
So if you yeah, from the point of view of Berkovitz formulation, it is exactly that. Yeah.
Okay. Thanks.
Yes. Well, yes, probably you see that on the slides. So if you look at these by expanding in a basis, so you can compute the pure spinor logs, which correspond to this commutator over here, and this corresponds to 4 quadratic equation. You can sum and subtract this, and you will end up with this 2 condition over here, which basically say that either the Weil spinor are 0 or the the anti-Weil spinor are 0. So I want to give you another example, which in a sense it's even easier than this. So the model is a superpointary algebra for d equal 3 n equal 1. And Poincare algebra is even easier because you have just the odd part just consistent to a copy of the fundamental representation of SU2. So the spinor is just an SU2 spinor. And the thing is, in this case, gamma defines this isomorphism. So second symmetric power of S is isomorphic to V. So, well, if you think about it, this implies that the pure spinor constraint is satisfied if and only if Q is equal to 0. And well, this is a little bit unsettling because you might think, well, okay, but then this space is absolutely lame, not interesting at all. But it's just like this as an algebraic set. Because to a closer look, so we have defined it as a scheme, and as a scheme is a fat point. So to a closer look, the constraint reads like this. So the quotient that you consider is this quotient here, and the space is the spectrum of this quotient ring over here. So you still have interesting modules that lives on this scheme here. So you have interesting module going on a fat point, as we know. And indeed, this theory does have interesting multiplex of fields. And this multiplex of fields can be constructed out of this. So, well, why I wanted to discuss this example, somehow I wanted to discuss this example because I want to somehow convey the idea that it is sometimes wrong to look at construction in a most naive possible way, but you should be a little bit more sophisticated when looking at this kind of variety in spaces, okay? So, for example, yeah, again, in this example, so looking at this just as an algebraic set, that would trivialize the whole thing. Right, so, okay, so we have, of course, a network of relation between different nilpotence varieties, which mirrors relation between different supersymmetric theories. So for example, so let me just discuss the vertical arrow. So the vertical arrow correspond to dimensional reduction. And from the point of view of nilpotence variety, so this just means that you discard some of the defining equation of the nilpotence variety. So you see that the embedding space, which is the projective space that you can see up there in the slide, does not change. Okay. Well, the dashed arrow is a little bit less intuitive, but basically is something that realizes the nilpotence variety that you see on the left-hand side as an hyperplane section of the one that you can see on the right-hand side. So basically, you set one of the coordinate to 0, one of the coordinate in projective space to 0, and there's a whole network of relation between these spaces. So some of them are really easy, other are more complicated. Please.
Is this vertical arrows connected to the post-programmer Hunter?
Sorry?
Vertical arrows, does they connected with the post-programmer Hunter?
Yes.
Okay.
Yes, they are, exactly. So somehow you can trace back something like this. Exactly. Yeah, Duflo-Serganova functor basically construct, so from the point of view of physics, construct the well, the twist of a theory out of a higher dimensional, higher super algebras. And so another example, well, okay, I'm getting lost with the, I'm losing a lot of time on geometry, but that's somehow what I like. So somehow a less trivial example. So you can think about this notion of nilpotence variety also for other kind of super algebra. So so far I focused on superpointary algebra, but how about simple super algebra? So this turns out to be very interesting because, for example, superconformal algebra in D equals 4, or better is complexified version, is isomorphic to the superalgebra SL4/n. And the information about the algebra are basically packed into metrics of the superalgebra, like you see in the slide. So the even block are the conformal algebra and the R symmetry, and the part are the supercharges. So you can wonder what does it mean? So what's the nilpotence variety of a superconformal algebra like this? And this is actually very interesting because this would somehow parameterize the twist of a superconformal field theory. Okay, turns out that the equation which describes this nilpotence variety are really easy, and they're given by this system of equation here, which is just AB. This is basically a matrix equation, AB equals 0 and BA equals 0. And indeed, the nilpotence variety is given by a pair of matrices that satisfies this constraint here. So how to study this? So of course, this is a convenient prescription if you want to basically put your hands on. You might want to have a more abstract description of a space like this, and that's of course possible. And first off, you can realize that you have a natural GL4 cross GLM action which fixes the locus of this, and you can use this to study this variety, and you would immediately recognize, well, basically these are rows and columns operation. So this is the stratification of the variety by rank of A and rank of B. So in other words, you have a diagram like this, where this y 1, 0, 0, 1, etc., are basically the strata that satisfy this rank condition over here. And the full nilpotence variety will just be the union of this strata over here. In particular, the union of the top component over there will give the full structure of the nilpotence variety of the space. So let me stress again that this first step tells you that the variety is singular. So just the fact that the variety is not irreducible makes it singular. And you can go on and wonder whether there's in a sense, a transcendental description of something like that. So I don't want to lose too much time on this, but you can find something like this if you think that the rank K matrices describes or defines a complex manifold. And the condition, so if you fix a point on this, this complex manifold of rank K matrices, you realize that B belongs to fiber of a particular vector bundle, in particular the conormal bundle over the variety of the complex manifold of rank A matrices over a point A, if and only if AB equals 0 and BA equals 0, which are exactly the defining relation of the nilpotence variety for this algebra. So in other words, a transcendental description of this variety would go like this, so or better, of a component. Would say that the component is isomorphic to a certain closure, it's a risky closure of the conormal bundle of the variety of rank K matrices inside the, well, the natural embedding space for this bundle, which is the cotangent bundle of the matrix 4 cross n. And again, as I say, this is related. So this variety here is related to the twist of superconformal field theory. This is what my fellow physicist collaborator explained to me. So let's go back to pure spinors. This was a big tour. So as I said, pure spinors. So philosophically, pure spinor superfield formalism takes a geometric object and yields a physical object. So how does this work? So the pivotal construction is that of a nilpotence variety, because we need to look at the module defined on the nilpotence variety. Okay, so I'll now go through this machinery, this particular machinery. So the first step is very easy, and you start basically constructing a supermanifold, a very easy split supermanifold out of the supertranslation algebra. So you just take the coordinate over the supertranslation algebra. And this means that your supermanifold will just have a structure shape, which is C infinity function over CDD, so space-time, as we interpret it. Tensor with the exterior algebra over the odd part of the supercongruent algebra. So, and we can call local coordinate of this gadget x and theta as we're accustomed with. So it turns out that there are two computing actions of the supersymmetry algebra on this supermanifold. I call it one L and the other R. That goes like this, and we will use both of them. So remember that these are available for us. So as I say, somehow a very important step is to take a module on the nilpotence variety, which means that we are looking at an Armodine module, okay, where I is the ideal, again, cut out by Q, by the commutator of Q with itself equals 0. So the crucial step is to tensor this module with the algebra of free superfields. So in other words, with the structure sheet of the supermanifold that we have just created. And this automatically gives a cochain complex. So why is that so? Well, we can define a differential on this guy by basically tensoring lambda alpha, okay, which is something that acts on M, because we Hermodite structure with the with the right action of the Q's on the supermanifold. So if you compute this guy, you would immediately find that this is 0 because we're living on the nilpotence variety. So this guy cut out. This guy is exactly the nilpotent, the nilpotent variety PL. So the pure spinor constraint, as you prefer. So if you look at this cochain complex, so this comes with a structure of the BGS vector space. If you define certain degree, if you want, on the coordinate, so the natural choice would be this. Notice that pure spinors has odd parity. So in a sense, it is natural to interpret this as the global section of an affine DGS vector bundle that has typical fiber that goes like this. So K refers to the Gauss degree. And this gets us very close to the notion of multiplet as I introduced. So multiplet was an affine DGS vector bundle together with a certain action of the symmetry algebra that we're looking at. So how to introduce this, so how to prove, in a sense, well, yes, how to prove that you do have such an action on this guy. So here you can use the other action, L. So indeed, the other action here will induce, it turns out that it does indeed induce the right action. So the action of the algebra G that you're after. And indeed, this construction defines a multiplet in the sense that I described earlier on. So in a nutshell, the pure Spinor superfield formalism takes graded equivariant modules on this nilpotent variety, and it yields P multiplet, but this very abstract notion of P multiplets, which sadly is still quite far from the physics, basically the physical intuition that we have of a multiplet as a certain collection of sections that transform in a certain way. So this is still very abstract, and it is still very abstract because basically it lives on superspace. So the notion of multiplet that I gave is something which is defined on superspace, while in a sense we automatically think about multiplets as something that lives on spacetime. So how to get something like this? So one can get something like this using, well, basically using some baby homological algebra and some spectral sequence machinery. So the thing is that we have given our x, theta, and lambda some degree, and in particular, our pure spinor complex A bullet of M as a filtration by this degree that we assign. So in particular, we assign this degree that you see in this tab, and so in particular, we can assign this filtered weight to our gadget x, theta, and L. So when one has basically a filter complex, one automatically has a spectral sequence related to this filtration, and computing this spectral sequence, one gets information about basically multiplet as understood by physics. So as a collection of sections that transform in a certain way under G. So notice that assigning weight in this way, so given filter weight 0 to the x, so C infinity function plays no role in their filtration, so it comes along for the ride. And from this point of view, you see that this is a digest filter vector bundle over spacetime, which is what we want. So the thing is to compute the spectral sequence that comes out of filter weight assigned like this. So first thing is to look at the differential. So one should realize which part of the differential basically descend. You see that the first part has weight 0, and the second part is weight 2, with a degree that with a filter weight that we have assigned. So basically, the graded complex is only equipped with the first part. So if one unpacked this information and write down the graded complex associated to A bullet of M, one finds out that this graded complex is nothing but the Koszul complex of the module M. Koszul complex is just this guy over here equipped with this differential here. So in other words, computing the first page of the spectral sequence, which is associated to this filtration, is nothing but computing the Koszul homology of M. And this is what gives the link, the relation. This is what basically puts in a relation A bullet of M. So this very big complex over superspace to well, basically the notion of multiplet that basically physicists have. So this new page, the first page of this spectral sequence indeed yields the component field description as it is known in physics literature. So basically, in order to make contacts between this A bullet of M, this big complex, and physics, so you need just to compute the Koszul homology of M. Yeah, we can skip this. So in a nutshell, you start with something very big. which is free over superspace, and you resolve it freely over space-time. And when you have resolved freely over space-time, so in other words, you have computed this causal homology, this first page spectral sequence gives the field content of the multiplet, as understood by physicists. First page differential will be the BRST or the BV differential, and the action of the Q on the representative on this homology will give the supersymmetry transformation in a sort of automated fashion. So you can go up computing homology, and of course you have a second page, but this no longer gives a notion of a multiplet, because in general you are not getting vector bundle by sheaf instead, so you have some constraint. Please.
I have a very basic question. So this sentence, so then let's say the typical property of homology, right? Is that regular sequence explanations. So in this sentence, do you still have, like, for this type of structures, you also have the same type of problem?
Yes,
I see. Absolutely.
absolutely. That was a good question, but so some example. Again, I introduced early on this the Nilpotence variety for n equal 1 model, which was just a copy of C2 which intersects in the origin. And so we can use this to compute some multiplets. So again, as I say, the point is to compute the relevant causal homology, but first we need to choose a module that lives on this guy. So for example, we can make this choice, which would correspond, well, geometrically to the push forward of the structure sheaf on the second component. And if you choose this module here and you want to compute the causal homology of this guy, you would find something like this, okay? But if you look at the differential, you would immediately realize that this basically doesn't see this part here, which factors out. Well, together with, of course, the dependence on space-time, so smooth functions. And you're left with basically computing the causal homology of this guy, which is acyclic, and just gives C. Easy. So if you reinstate the dependence, and I mean, this is, I think, a nice example because you can basically carry out all the computation by hand. So you don't need any kind of technology to see this. So if you reinstate the dependence on space-time, at the end of the day, your multiplet would read as something like this. There's an obvious interpretation for something like this. And this is the chiral super multiplet of D equal 4, n equal 1 theory, which indeed contains one scalar field, one spinor field psi, and an auxiliary field F. Right, and of course you can also look at the how much time I have? Not much, I think.
About 10, 15 minutes.
Okay,
Because
fine.
some delayed occurred.
So yes, of course you can look at the action of supersymmetry transformation of this, and this gives basically the ordinary thing that you would find in physics textbooks. So would read like this. Notice that this differential here is now the twisting differential. So if you apply this 2 times, it's 0. And we can compute the twist of this theory. So in particular, the twist of D equal 4 n equal 1 theory. It's of this multiplet here is a holomorphic theory. So allow me to just give a slightly more juicy example, which is supersymmetry in 6 dimensions. So this model, so in this models, you have that basically the odd part of the super Poincare algebra is described is given by symplectic spinors. So in particular, you see that U that you see in the slide is a two-dimensional symplectic vector space. So you might wonder, how would the pure spinor equation look like? And it turns out something that is geometrically quite pleasant, that the basically the nilpotence ideal is a determinant of ideal. So it is given by the 2x2 minors of this linear form here. So in other words, it is the rank one locus of L. So, well, the linear form is of rank one if L is the Kronecker product of two vector x and y, which automatically basically tells you that if you look at this form, the projectivization of the nilpotence variety will be where the cross product of B1 and B3, which is a Segre, which is a Segre variety, which is naturally embedded in B7, which is basically the projectivization of these 8 guys that you see here. Okay, and that's very pleasant, of course, because, for example, so in order to run our say machinery, so we need to know some bundle, or we need to have the description of module on this nilpotence variety. But something that we know for sure on a manifold like that are line bundles. So line bundles, if you basically compute the Picard group, which is basically which basically classifies line bundle on this variety here, you find that the Picard group of this Segre variety is 2 copies of Z, meaning that the only line bundle that live on this space are line bundle that comes from this and line bundle that comes from this. And this line bundle are just the basically the exterior tensor product of indeed line bundle on P1 and line bundle of P3. And usually they're written like this. Okay. And these are very easy objects. The cohomology of these guys is completely known. So you can compute a lot of stuff using this line bundle. In particular, you can run your basically your algorithm to construct multiplets for all line bundles on the nilpotence variety. And already in the basically most basic case for the structure sheet for this hyperplane, for this hyperplane bundle here and for this other bundle here, you find very interesting multiplets. So in particular, the structure sheet yields what is known as vector multiplet, because you find something that transforms as a vector, so section of the tangent bundle over spacetime. That the hyper multiplet, which has this somehow this symmetric structure over here, and this guy is the anti-field multiplet of the vector, because basically it has the same content if you basically read the field content from right to left. And indeed, well, anti-field multiplet, as you can imagine, as my this friend explained to me, is basically crucial to construct. So basically to move from cinematic to theory, because you can construct BB action by pairing in a suitable way a multiplet with its anti-field multiplet. So you have some kind of pairing that allow you to write action. So notice that so this doesn't really want to be some kind of advertising, but notice that this pure spinor machinery is kind of convenient. So if you look at the paper in physics, so a single paper deals with basically the construction of a single multiplet like this. But this machinery, in a sense, gives you all these multiplet at once. Okay, so in a sense, it is a unifying framework to construct things like this. So we, all right. course, you can also consider higher rank example. And an example that I like is that of conormal bundle. So conormal bundle fits into, well, the conormal bundle exact sequence that in the case that we're looking at for the Segre manifold P1 cross P3 and P7 would look like this. And if you compute, if you run your pure Spinor algorithm for the conormal bundle, you would find exactly the field content of the so-called supergravity multiplet. Why supergravity? Because inside the field content, you find a graviton and a gravitational field over here. Something that I don't know, something that I cannot really explain to myself is why, if you consider conormal bundle of nilpotence variety, you always find the supergravity multiplet of the related physical theory. So I don't know why you do have something like this. You do have this kind of correspondence. Mainly, I thought at first that you would have gotten something like this out of the tangent bundle, but not the case. So I'm about to conclude. So as I said earlier on, somehow the dialectic between fields and antifields is relevant from multiplets to theories. So a good question in this sense is, okay, so I find a multiplet. So how to construct antifield multiplet giving a certain multiplet? So in other words, what module should I pick out if I want the antifield multiplet of a certain multiplet that I found? So it turns out that the situation is twofold. So there's the good case that goes as follows. So if the module that I choose is a Cohen-Macaulay, well then the dualizing complex of M is the right gadget to look at if one wants to get the antifield multiplet of M. Notice that basically, okay, Cohen-Macaulay is a condition that tells you that somehow is a homological triviality condition. It says that some X group are 0, except for, well, basically all the X that are 0 except in 1 degree, which basically corresponds to the dualizing module of that very module. So that's a good case. And in this case, the machinery that I explained work, and it's fine. But there's a bad case that appears when M is not Cohen-Macaulay. So in this case, one truly cannot construct the antifield multiplet of a certain module M. Basically because in this case, so if the module is not Cohen-Macaulay, so the dualizing module is not a module, but it is a complex. Because one might have several X group of the module which are different from 0. And basically, basically the dualizing complex is spread out several degrees. And the machinery that I explained is not capable to deal with complexes. It's only capable to deal with modules, so a single module. So this hint upon a certain direction to pursue, which is that of derived geometry. So a formalism which would be capable to deal with complexes instead with a single module. Okay, and notice that this is not, well, something very exotic, but if you consider the structure sheet of the example that we saw early on, so E equals 4, N equals 1, well, that guy is not Cohen-Macaulay. So the instance in which you cannot construct the antifield multiplet of something by a pure spinor, it's something that actually appears in a realistic physical model. Very basic one. And there's a far from being complete, say, dictionary of properties, algebraic properties of module that translate to somehow physical properties of multiplet that mirrors the fact that a certain module is more or less regular more or less beautiful in a sense. So again, from the somehow from very nice module to module which are not so nice, you have somehow multiplets which are very easy to multiplets which are not that easy to deal with. In particular, you have, for example, for not chemical like module, you have no anti-field multiplet, or at least you do not have anti-field multiplet in this way. I think I'll stop here. Thank you very much.
Okay, thank you very much. Thanks for nice contribution, and I think there's a little time for some questions from the audience. So please.
Please.
I have a couple of questions. There's no time. So usually in physics literature, the pure spinors, at least like let's talk about 10 dimensions. It's said that they parameterize some cosset space, which is like S of 10 divided by 5.
Yes.
And so is this what you get for the Nilpotence variety?
No.
Setup?
No, but that's a very good question. So that in that case, so that is basically related to the name pure spinor in a sense, because okay, pure spinor is something that Cartan introduced, and a pure spinor. Okay, so may I use the letter?
Yeah.
Which one? So let me see if I remember correctly. So so if you think about a spin representation S. So this is a Clifford module. So this means that, well, of course, you have an action on S, and in particular, you have an action of B on S. So you can think about so you can pick up, so say that you have a field in S. And you can think about the annihilator of Q. It's just a V in B such that B Q is equal to 0. Okay, so in general, if the dimension, say the complex dimension of B is say 2n or 2n plus 1, of course this is lesser or equal than this dimension, and in particular, you find out that this is n, which is lesser or equal than n. So in the particular case, this is n. So if this dimension is maximal to this zone. So basically, you're dealing with the maximal isotropic subspace of B. So in this case, you have exactly that condition, and these spinors, these Q, are called pure spinors. And pure spinors indeed comes about from a quotient, so there are homogeneous spaces that, as you say, are like some SO, I think, say some 2n mod U and something like this. But this happens only in some cases, and basically the name of the whole machinery is, well, let's say just an historical name, because basically the model was constructed to deal with a 10-dimensional example. But for example, the case that I explained, say 6th dimension, well, that is far from being like a space like this or something, and several other models do not correspond to a framework like this. So you're far from something like this. But yes, that's the relation in a sense. So these are, so basically this condition are pure spinors as Cartan described them. So the minimal orbit of S in the projectivization of B. Yes. Please.
Maybe I have a question about trying more representation survey and not much more. It was Garner Hunter. So when he was drawing this diagram of important variety for a classical, so taking any guy from the important variety, you can consider new leaves of algebra. You take its image over the kernel of vice versa. And from that point of view, all guys in the diagram that lives on the same horizontal levels will give the same D algebra, so kind of glue them together.
Yes.
But will you see the difference on these horizontal levels from the point of view when you consider the corresponding multipliers?
That's a good question. Well, in a sense, I would say that I see the difference from the point of view. So to relate this to, for example, the Duflo-Serganova functor, I would say that I see this difference somehow mirrored in physics from the point of view of a twisted theory. Because, so for example, if I consider a rank 4 guy, so top level, and I twist the theory with well, let's say a coin that lives there, so a supercharge that lives there. So somehow this so you would say that so the Duflo-Serganova functor would tell me, for example, that that I'm basically pushed down to basically by 4 exactly. And this turns out to be a topological theory. Basically, so if I twist by the highest possible rank, I land on a theory which is topological. If I twist by, well, for example, the lowest possible rank, I usually, so for example, 1,0 or something like that, I usually land on a theory that basically make exact a part of the field. In particular, for example, in the example that I gave early on, say holomorphic or anti-holomorphic. And that's what is called holomorphic field theory, or like anti-holomorphic field theory, which is in a sense isomorphic. So that's probably the connection that I see. From the point of view of multiplet, that I wouldn't know.
I also was curious, mainly when you look somewhere in the middle, for example, for SL case, when you take a rank of A is equal to A, well, yeah, B. So from the classical Garner functor point of view, you will see everything that when everything will be the same for A and plus B equal to the same number, but it will be different.
Different stratum of, well, that's well, I guess that is because like, well, in a sense, this you do have some symmetry in that well, let's say that diagram that I drew, and you indeed have a sort of a mirror symmetry by well, let's say reflection symmetry, and indeed some strata are actually isomorphic, and that's possibly related to, I guess that's related to what you see, that it's basically the same thing to take one there. But yeah, to be frank, I'm not an expert in like representation theory. So somehow the relation that I see with the Duflo-Serganova functor is indeed with this twisting procedure that exists in physics. And I confess I don't know.
There is one question apparently from the online audience. So,
yes, thanks a lot. Thanks for a great talk. I have a question that it's probably not very related, but I was wondering if you have a notion of expectation values of an observable here.
I don't think so. No, I don't think so. Sorry, what do you mean by expectation value? So you mean so you're referring?
I think that compared to the case of superspace, where I can write down a path integral and evaluate an observable thanks to the path integral. Then
Well,
here, what do you do?
Okay, I got it. So I would say that in a sense, this framework is still kind of far from that. In a sense, it constructs, well, if you want the building blocks to write down action, enhance path integral for actions. Well, again, in a sense, one of the problem is that to move from, in a sense, multiplet to theories, one needs some further data, which in good cases are, in a sense, built in the multiplet, because the multiplet is really beautiful. So it somehow comes with a pairing that allows you to write an action or something like this. But in general, there's no such a notion built in. So you don't have automatically like an action or enhance the notion of expectation value of out of this. So I would say that this is my answer, which is of course not quite satisfactory, I guess.
Thanks. Anyway, that was nice. Thanks.
Okay, so any other question, either from online audience or from you?
Yeah, maybe I see that.
Sure.
Okay, so before going quantum or evaluating path integrals, my question is on equations of motion. So we saw how to build a super multiplet or a multiplet, a set of fields from the physics point of view. So can you derive in this approach of the equations of motion? Because in usual Spinors construction, you can. Right?
Yes, it works pretty much in the same way, I would say, except for if yes, it works pretty much.
So you act on superfield and you impose it zero.
Exactly. So basically, this comes in a sense for free. Well, this comes for free. Somehow you trace this back to the very action of G. So in a sense, if this does not close this initial element, you ultimately find terms, which is related to the equation of motion. And that's basically exactly what you say. So basically, this is d of zero. Yeah, from this point of view, I wouldn't say that this is much. This better.
Maybe I would have one question. I'm not very familiar with module theory, but what's the distinguished property of those modules you've described at the last slide? Yeah. Which?
Well, so okay, so there are somehow there are many ways to characterize the Cohen-Macaulay module. So probably the most efficient way to do that in connection with this talk, as I mentioned, is to think about a computation of X module related to the module itself. So imagine that you have some so S inside some air. Okay, and oh, sorry, I can move.
No problem.
So maybe you have something like that, and imagine that. Well, you can give a notion of dimension. So if you're in algebra, you would speak about crude dimension. So basically, we can prove that a module, so this S would be a Cohen-Macaulay module. Here.
And sorry, R is what?
Sorry?
R there?
R, this would be a Cohen-Macaulay module.
Okay.
Cohen-Macaulay R module. If this guy, so say that over here you have stated that you have you can compute this guy. So for this guy. And turns out that is conical, right? If this is non-zero, only in a single degree, which in this case, so non-zero, if and only if I basically equals the codimension. So it's n minus 1.
So this is a kind of direct consequence why you are not forced to compute it in a derived setting.
Yes. So you see that, well, in a sense, this gives some module.
So this is the definition. Or
you can think of this as a definition. So usually the definition is given in a different framework, which is in a sense less that, well, let's say that in order to make contact with the actual definition to this one would take some time. But for this context, this is in a sense better because it immediately say that somehow tells you that something which is basically in a geometric situation, the dualizing module, because you can think, so if this is a smooth thing, you can think of these guys as basically differential forms on S. Okay, and this would be basically top forms. And top form are canonical bundle or dualizing module, call it as you prefer somehow. So if this is not zero, if this is different than zero in more than one single degree, so this guy that you call like dualizing complex is spread out in several degrees. So you don't truly have a module, but you have a complex instead. So basically, indeed, you don't have a single module, but you have complexes, and then you need to be able to deal with the complex of modules. So you need a machinery that deals with complex. So this is something that we can do. This is basically the yoga of derived geometry. So it's nothing exotic. But for example, you need to improve your formalism a little bit to introduce a notion of derived pure spinors that is actually capable to deal with these complexes instead of with a single module. So this means that, well, your nilpotence variety will not be a scheme, will no longer be a scheme, but it will be a derived scheme. So the spec of what? Of a complex.
Okay.
Instead of a single, instead of some R modality, something like that. So that's the thing. And sorry?
I mean, do you understand correctly that your reformulation is calling property says that as a depth is equal to the cruel dimension?
Yeah, it should be like that. Yeah. So but well, to be completely frank, I would definitely not be able to prove that on the spot. But yes, exactly like you gave the ordinary characterization of coin-collect property for a Noetherian local ring. Yeah, which is that is. How to do that? So Slander Books one formula tells you something, and I don't think I could be able to come up with a proof like that. But I'm pretty sure about that.
I think we are run out of the time. So thanks again for nice explanations.
Thank you.